Okay, so we're going to talk about comparing sets. So set equality says that two sets, A and B, are equal if they are exactly, or they have exactly the same members. So that means set A is equal to set B. If A and B are not equal, then we're going to put a line through it, like we've done in the past, for whether it was an element or an element of, not an element of. So A does not equal to B means they're not equal. Now equivalent, sets A and B are equivalent if the number of elements of A is equal to the number of elements in B. Remember, this is like doing the cardinal number. So the number of elements is the same as the number of elements. That does not mean that what's in set A is the same as set B, just the same number of elements are in set A as there are in set B. Now a subset is a set where all the members of one set are also elements of another set. In other words, set A is a subset of set B if every element of A is also an element of B. So A is a subset, that line underneath it is equal to. So A is a subset or equal to B. Not a subset, A subset or equal to, it has a line through it. So that means, again, not. Now the empty set is a subset of every set. So the empty set is always going to be a subset of that because it's a subset of every set, no matter what it is. So this is a Venn diagram. This would be where B is a subset or equal to A. That means all of set B is inside of set B. Now it could also be the same. In this case it's not. It's smaller than that, so it's not A. A proper subset is that set A is a proper subset of set B if A is a subset or equal to B, but A is not equal to B. So A would be just a subset of B. So this is an example of that B is a proper subset of A because it is a subset of A, but it's not equal to A. So you could write it as that, as a proper subset. I'm not going to care which way you write it, so just be aware of that. I'm not that picky. So A, if it's not a proper subset, then you would do that. And then the number of subsets of a set with k elements has 2 to the k subsets. So now I've got the vocabulary out of the way. Let's go look at some examples because that's where we're really going to learn what's going on. So for example 1, we're looking at set equality. Okay, so we're looking to see if the pairs are equal. So for set A, or for part A, we're looking at the set of Facebook, Flickr, Twitter, Pinterest, Instagram, and Vine. Okay, now let's look at the other set to compare it. So we have Pinterest, Flickr, and we have Instagram, and we have Twitter, and we have Facebook, and Vine, and Flickr, and Pinterest. So I realize I capitalized some and not others. It doesn't matter in the capitalization. We're not going to look at that. So are these exactly the same? So these are the same because they contain the same elements. They're not in the same order, and some of them had repeats. So Pinterest is in here twice, Flickr is in here twice, but otherwise the elements in there are the elements in there. So these sets are equal. Okay, let's look at part B. So if we have P is equal to X such that X is a letter in the word listen. And we have Q is equal to Y such that Y is a letter in the word silent. My glasses fell off again. They're getting kind of stretched out. All right, so are these equal? Well, if we look at the letters of listen and silent, they're all the same letters. We can state that P is equal to Q, which is equal to L, comma, I, comma, S, comma, T, comma, E, comma, N. Those are the letters in each of the sets. L, I, S, T, E, N, and silent as well. So they are equal. Even though they look like they're not equal, they really are equal. So that's an example. Those are two examples of equality. Let's go look at equivalent. So if we look at example 2, we want to know, are they equal or equivalent? So if we look at part A, we have A, B, C, and D, the set containing those. And then we have the set of D, B, A, C, and D. Now, are they equal or equivalent? So let's go back again and look at our vocabulary. So remember, equality means that they have exactly the same members. Equivalent means they have the exact same number of elements. So the same elements, the same number of elements. So let's go look. 1, 2, 3, 4, 1, 2, 3, 4, 5. This one has, but it actually has the same elements are in there. This one has A, B, C, D. This one has D, B, A, C, D. So they have the same elements, the exact same elements. This one got repeated again. So this we will call equal because they are the same elements in there. If we look at part B, we have the set of 1, 2, and 3, and we have the set of 4, 5, and 6. Now, they are not equal because they have different elements, but we can look at this has 3 elements, this has 3 elements. So the number of elements is the same, so we call this equivalent. Equal is exactly the same. This is equal to that. A banana equals a banana, an apple equals an apple. Versus the number of pieces of fruit in this basket equals the number of pieces of fruit in that basket. So there's the difference of what you're looking at. Equivalent versus equal. All right. So let's look at something that is not maybe the same. So let's look at part C. What if we have the set 7, 9, 11, and here we have 8, 10, 12, and 14. Well, the elements here are not the same as the elements there. The number of elements, 1, 2, 3 elements here, 1, 2, 3, 4 elements here, well, they're not equivalent either. So this would be a case where they're neither. They are not equal sets. They don't have the exact same things and the same number or count of what's in there is not the same. So this would be a case where they're neither equal nor equivalent, just to make sure we have that as clear. All right, so example 3, let's go look at some subsets. So if we have A is equal to 1, 2, and 3, and let me make sure I clarify, we are identify subsets. That's what we're trying to do here. And we have B is equal to 1, 2, 3, and 4. So remember, a subset is where those elements are all in the set of the others. This one set is inside of the other set. So remember, we can look at that as a Venn diagram. All of this one was inside of that one. So we're looking here to see, is one set inside of the other? Well, if I look at this, all of 1, 2, 3 are inside 1, 2, 3, 4. All of these exist over here. So that tells me that A is a subset or equal to B. Now, can I say the same thing, that B is a subset or equal to A? Well, if I look at, are all of the elements here inside of A? Well, most of them are, but the 4 is not. So this would be that B is not a subset or equal to A, because this one's got 4 elements in it. That one's only got 3. And so that number 4 is not inside of there. So therefore, it's not. Okay? All righty. So let's go look at example 4. So for example 4, we want to find all subsets of the set 1, 2, 3, and 4. And we want to do this systemically. Systemically. Okay? Which means we want to use a system. Systematically might be another way to say it. All right. So, first of all, let's make a chart. So we're going to do the size of the subset, and then we're going to have the subsets, and then we'll have the number of subsets. All right, so first of all, the size of the subset, remember, there is the empty set is always a subset of every set. So first we're going to have 0 members in our subset, would be the empty set, and there would be one of those. Then we'll look at all sets with, or subsets that have one element. So that would be the singleton set of 1, the singleton set of 2, the singleton set of 3, and the singleton set of 4. So we have 1, 2, 3, 4 of those. All right, let's do the sets that have 2 elements in them. So that means we have 1, 2, 1, 3, 1, 4. So I find it better if I just start with the first one, keep it the same, and go through the rest. Now we'll go on to 2. So 2, 3, and 2, 4. So we're going to, for this purpose, we're not going to go and then 2, 1. 1, 2, 2, 1. In this case, because we're not being specific of first element, second element, that means the same thing. So don't repeat ones that are already that way. So I did all the 1s, now I did the 2s, now let's go do the 3. So 3, 4. So how many do we have? We have 1, 2, 3, 4, 5. We have 6 total subsets. All right, let's go do the subsets that have 3 elements. So we have 1, 2, and 3, 1, 2, and 4, and then starting, so that's done all of my 1 and my 1, 2s. So now let's do the 1, 3. So 1, 3, and 4. So now I've done all of the 1s. Let's go do the 2. So 2, 3, and 4. And that's all there is. So we've got 4. And then we can have the subsets with 4 in them. So we'd have 1, 2, 3, and 4. And that would give us 1. So what is our total? Well, we've got 1 plus 4 is 5, plus 6 is 11, plus 4 would be 15, plus 1 would be 16. So there would be 16 total subsets in our, when we're looking at all of the subsets there. Okay? So that's systematically, we're looking at using a system to actually create how many subsets we have. This will be something you'll see in homework and probably see something similar to this on an exam. All right, so now let's go look at another example. Using this, what we've learned here, okay? So here we found all the subsets. Let's generalize this, okay? So if we want to generalize the number of subsets so that we can kind of see what's happening. So if we want to do that, I was trying to see if I could figure out, but I made my lines a little too long, so we'll just go to a new sheet. It's fine. So we want to generalizing the number of subsets. So we're going to call this our subsets. We're just going to do just an S. All subsets of S, and then the number of subsets of S. All right, so if we just have, if our set contains the empty set, then we have just the empty set. If we're just the empty set, and we have one member. If we have a set that has one element in it, and we're just going to use the number 1, it could be anything, but we're looking at 1, then we would have the empty set, and we would have the set containing whatever that number is. And we would end up with 2 subsets. If we have a set containing 2 numbers, or 2 elements, we would have the empty set, we have the singleton set of each one, and then we have the set containing both of them in there. So we end up with 1, 2, 3, 4. If we have a set containing 3 elements, then we have the empty set, we have a singleton set of each one, we have the singletons, or not the singleton, but the sets with 2 elements, make sure you use curly brackets, not parentheses. And then it would have, so 1, 2, 3, 4, 5, yep. Then we have the one with each of them. So we have 1, 2, 3, 4, 5, 6, 7, 8 sets here. Now, if we look at the one that has the 4 elements, which we just did, and I'm just going to write example 4, because this is example 5. On the previous example, we found that we had 16. So what do we know what's happening here? Well, we have 1, 2, 4, 8, and 16. So if we're looking for a pattern, it's 2 to a power. So if we're looking for the pattern, if we have 2 to the 0, remember anything to the 0 power is equal to 1. If we have 2 to the first power, well, that's 2. 2 to the third power, 2 to the second power is 4. 2 to the third power would be 8. 2 to the fourth power is 16. So we could think that 2 to the fifth would be 32, and so forth. So if you can see the pattern, so 2 to the 0 is 1, 2 to the first is second, 2 to the second is fourth, 2 to the third is eighth, 2 to the 16th would be, or 2 to the fourth is 16, and so forth. So if we have a set, if we have set A is equal to 1, 2, 3, 4, 5, 6, 7, 8, and 9, could we figure out the number of subsets in set A? Well, without writing them all out, I can use this. This is what in your handout talked about. The number of subsets of a set with k elements is 2 to the k. So if I have 9 elements, I can go 2 to the 9th will get me 512 subsets. And that will work for however many number of elements that you have. All right, so let's go look at example 5. So just remember that 2 to whatever number. So actually this would be example 6 because that was example 5. So example 6. So we're going to do the counting subsets by drawing a tree diagram. So we're going to count subsets by drawing a tree diagram. So kind of like what we've done before. So we're just going to keep it simple. So we can look at the set containing A and B, and we want to construct the subsets as making pairs of choices. So we're always going to start with that. Even if we don't have a label, it's got to start somewhere. And then we want to look at choose element A, and we're going to call that yes or no. So those will be our choices, yes and no. Whoops, got to hit my dots. And then we'll look at choose element B. So we're going to have yes or no again. So we have yes and no. And here we'd have yes and no. Now you could also look at A and B, and then from there you choose, but if we're just looking at choices. If we choose A and then we choose B, like what would that look like? So let's kind of go along. So how many are we ending up with? Well, we're ending up with 4, which we know is the case. We have 4 choices here, and we know that will happen because if we have 2 elements, we've already figured out it's going to be 4. And we know that two sets, that's 2 or 2 elements, 2 to the second is 4. But let's see what that would look like. If I choose A and I choose B, that means my first set would be A comma B. If I choose A and not choose B, I would just have the singleton A. If I don't choose A, but I choose B, then that would be B. And if I don't choose A and I don't choose B, that would be my empty set. Just for clarification of what would that look like if I don't choose them or I do choose them. So that's just another way you can kind of figure out how many subsets are there. Remember, we've talked about problem solving. There's many ways you can look at something to see which way it will work, to figure out what makes sense to you on how to solve a problem.